Uh, so these are some of the initial things which we did to compare the capacitors and the supercapacitors in terms of, like, as we all know, the capacitor, so which falls through like the capacitance range, uh, obviously below 1 farad, and then the working voltages like in the range of 1 to even about 1000 volts. So when we compare the capacitors with the supercapacitors, so this the right hand side in the figure here, which shows the energy, the amount of energy that can be stored in the same can size. So when we look at this, the right hand side, so you can say, like, so the in terms of the physical size, so the amount of energy that can be stored in a supercapacitor is relatively high with compared to the same the can size electrolytic capacitor. So for example, this one here, it's about 13.6 joule, and this is 365 joules. So it's just to like give the general audience bit of an idea how the capacity, the energy storing capacity of the supercapacitor. So these are some of the works like which we did to investigate the properties. As we all know, for the batteries, over the depth of discharge, the internal resistance which goes up. For supercapacitor, it's like pretty much remain constant for a long time. So that's some of the advantages. And this one here is again some of the calculations which we did to bit of a comparison. So these are some of the supercapacitors from LSM Tron. So where 3000 farad capacitor. So the one downside with the supercapacitor is the low voltage rating. So the one good thing is a very low ESR. So which you can see it's about 0.36 milliohm. And then we calculate the energy storage capacity, which is 10.9 kilojoules. So the maximum power. So for like if we work out for the ESR as the load, so which can offer 6 kilowatts. So so likewise, so we did a bit of a comparison here. So which is again this one is an electrolytic capacitor, so which is about 2200 microfarad, so which has a 50 volts, so which has the maximum power, which is 8.8 kilowatt. So you can see the supercapacitor which has been like pretty much close numbers getting there. And so for a like this one is a C-type, the disposable energizer cell, so which is about 1.73 is what is the maximum power. So it's just a bit of an actual number comparison instead of like just saying you the numbers, right? So this is a more common thing when you see everywhere the comparison of supercapacitors and their advantages. So it's more like the lifetime and the low ESR and the operating range. So with the temperature, it's much better. And also in terms of environmental issues, because the issues with the batteries, especially like the lithium-ion batteries and the harmful, the chemical compounds, and with terms of these things, it's still supercapacitors are much better with the environmental aspects, and the low leakage current. It's about 5 to 50 microampere leakage current roughly in supercapacitors. And the downside, so is the low working voltage, because it's come down to 2.5 to 2.7 for a supercapacitor, and obviously the high cost at the market. So it will come down because the bigger the application scope, it will come down. So that's how it is. So then, like, if I'm going to give you a bit of an overview of what's inside the supercapacitor. So actually what you see inside the supercapacitor is the electrodes. So the two electrodes and electrolyte. So there's a separator in the middle, as you can see this in the diagram. So that separator, so actually, which makes this becomes a two capacitors scenario. So what happened is the electro in this the arrangement. So when there's a separator in the middle and which is immersed in the electrolyte, so what happened is, so the negative electrode attract the the negative plate which attract the positive ions, and the positive plate which attracts the negative ions. So in that way it makes like two capacitors inside a single capacitor because of these ions attract to two different sides. So what you can see in this the figure, so what you say is like some sort of equivalent circuit. So the electrode, so which represent the resistance, and then there's one capacitor and the separator, and the electrolyte which represent another resistance, and then the other capacitor. It's more or less like that's what it is called electric double layer, because it has double capacitors inside. So like as usual, like the other the normal capacitor, it's the energy stored is the half CV squared, and the maximum power that you can get based on the maximum power transfer, which is V squared over 4R. So like probably as you see in the current the research domain and the market trends, so mostly these supercapacitors are being used as energy storage devices. And so especially in the automotive industry with the electric cars and then the hybrid cars and the eco-friendly like economic option and all these things with the supercapacitors due to the high power density. So it's being used in all these application areas. So actually this was some of the application circuits, so where the supercapacitor is used in the modern cars with the start stop function in the eco drive. So like actually our application scope in the supercapacitor application is a completely new domain. So which is some sort of a non-traditional applications, which is not fall through the normal like using a energy backup. Right. So I will pass into Nihal. So he's going to give you a bit of more details about what's happening in the supercapacitor, the market, and what are the new trends and what are the new sorts of supercapacitors available. And then after that, he will put you into the DC microgrid area, and then I'll come back and tell all the basic and then the application area that we are working on. Okay, I'll pass over to you, Nihal.
Okay, thank you, Kosala. Okay, now this slide shows you how you compare traditional capacitors like electrolytic and film capacitors on the left hand side, and on the other side you have the batteries. Now next to traditional capacitors you have the symmetrical supercapacitors, usually with the carbon activated carbon electrode on either side. Then they are what you call the electric double layer capacitors or ultra capacitors. Then within the last 10 years, the manufacturers were able to bring certain amount of battery properties into the symmetrical supercapacitors, bringing up what you call the hybrid type supercapacitors. So they are with one electrode like a normal supercapacitor activated carbon, the other one is lithium titanate like battery electrode, and then those are what we call the hybrid supercapacitors. Then more recently they brought lithium ion battery concept, but dominated by capacitive action, which are called the kappa batteries. So now this slide shows from traditional capacitors to batteries, they store more watt hours per kilogram or watt hours per liter, high energy density. But when you go towards batteries to traditional capacitors through these types, you can deliver more watts per kilogram. Like for the case of a car accelerating, your kilowatts per kilogram matters than watt hours per kilogram. So supercapacitors are ideal for very rapid high power delivery. Now in the next please, this shows the difference between traditional supercapacitor like this one. These are fairly large symmetrical supercapacitor, 3000 farads, 3 volts, where 2 electrodes are identical. So this is the older type of supercapacitor, which is represented by the left-hand side figure, which has 2 nearly identical capacitors. But in the newer types like kappa batteries, what you see is for the same CAN type, that 3000 farad capacity is now increased to 70,000 farads. So this is equivalent to about 35 to 40 watt hours in this capacitor. So this is getting closer to battery energy density, and this technology called kappa batteries, which is shown with asymmetric capacitor like on the right hand side, they are now very close to lead acid battery energy density. So now if I compare these two, for the identical CAN size, they have increased the capacitance by about 13 to 14 times. So these are huge capacitors. Now, if you charge one of these things, you can short circuit and get about 9,000 ampere short circuit current without damaging the capacitor. So this is the capability of these capacitors, hybrid type capacitors and the large supercapacitors. Next, please. Now, in this slide, we compare traditional lithium-ion rechargeable chemistry with symmetrical supercapacitors, or the old type of supercapacitors, hybrid supercaps, and the kappa batteries. So if you look at lithium-ion batteries, still provide you highest energy density, but their life cycle is only several thousand cycles, the best case, probably less than 2,000 to 3,000, and they can be operated within the temperature range of 0 to 60 degrees Celsius. So most electric cars are, if you have a very cold temperature situation, these batteries will create a lot of problems for electric cars. Now, symmetric supercapacitors can go from about minus 40 degrees Celsius to easily up to 60 degrees Celsius, and there are certain versions which can go up to 85 degrees Celsius light. And their life cycle compared to lithium batteries, they are between 500,000 to 1 million charge discharge cycles. So they are basically fit and forget devices. Now you move from hybrid normal supercaps to hybrid ones, your energy density is getting almost double compared to symmetrical ones, but their life cycles still drop to about 50,000, but still very large. Then their temperature range is minus 20 to about 60 degrees, whereas the newest types of these types of kappa batteries, they give you nearly energy density of lead acid batteries with a life cycle less than 30,000 cycles. But if you compare any type of supercapacitors with lithium ions, your life cycle is at least 30 times to 500 times bigger. So they are all fit and forget devices. So today, single cell devices are available up to about 70,000 farads. Next, please. Next, please. Now, actually, I'm comparing these three types of new supercapacitors, symmetric type old supercapacitors, hybrid types which came in around 2014-15, then kappa batteries which came in 2017 like. So if you look at the voltage versus discharge time at a constant current, the basic supercapacitor, the older type symmetrical supercapacitors have a constant current discharge shown by that blue graph on the left hand side, whereas the hybrid type supercapacitor 7500 hybrid gives you something slightly different as shown in the orange graph. But if you look at the Kappa batteries, it has the voltage time characteristic like rechargeable batteries flat voltage region. Now the same three capacitors are compared in right hand side with the constant resistance discharge. So in the symmetrical supercapacitor you get a near exponential curve, whereas the middle type hybrid ones have a capacitor form suddenly dropping. Then for the 40,000 farad large Kappa battery, you have the battery performance shown. So the Kappa batteries are more close to battery performance, whereas symmetric supercapacitors are more close to a normal capacity. Next, please. Right. Now, as we all know, batteries are tested with what you call the C rate. Now, if you translate the same C rate to these hybrid and the Kappa batteries, if you discharge them at 1 C rate, this is how the two different types of capacitors behave. So there you can very clearly see these Kappa batteries are more or less like rechargeable lithium-ion batteries performance, whereas hybrid types are little closer to the capacitor type, but still it is much better than a normal symmetrical supercapacitor. Okay, now let's go into DC microgrids and future prospects of DC operable electric grids. Now, it was in 2014, IEEE appointed the Energy Efficiency Committee for DC operation. So, I was in this committee as the vice chair, and when we released the report, we found there are a lot of opportunities for DC operable goods, because most of the modern white goods, including the inverter driven heat pumps, etc., internally they operate from a DC bus. Now, given the interior DC operation of these white goods and so on, most of these devices could be fed by a DC bus, but for which the manufacturer should allow the end user to feed DC into the thing, so which is probably coming in another 3 to 5 years. So now if you look at DC distribution systems in modern buildings, you could have 380 volts DC for high power systems and heat pumps and larger appliances. Then you could have an intermediate bus of 48 volts for telecommunications and other things. And for lighting loads, you could have 24 volts DC. So these three de facto standards, 380, 48 volts and 24 volts DC bus based DC microgrids are getting popular. That is why IEEE Power Electronics Society has now established a new conference series called ICDCM, International Conference on DC Microgrids, which were held in US 2015, 2017 Germany, and 2019 Japan. And from next year, it will be annually running. So that shows you how much the DC microgrids are getting popular in most countries. Typical situation is your photovoltaics, wind and battery supercapacitor energy sources are going through a common DC bus, and for the appliances where you cannot directly feed DC, you go through an inverter. So your loads could be lighting, PC loads, electric vehicles and white goods all at different, but so in some situations you can have only DC-DC converters than inverters when you use a DC microgrid. So now there are a lot of data centers in US and Japan like places where they use renewable energy sources directly feeding the DC bus inside the data center. One example is shown in here, this figure. Now, when it comes to energy storage, your energy storage options are batteries, fuel cells, electric cars could be a energy storage source, and for rapid power delivery, supercapacitors like this. So, future nanogrids, microgrids could be totally DC because you avoid one conversion interface from DC to AC to operate things from AC sources. Next, please. Now, to support these DC bus systems, today you can buy DC operable air conditioners, which operates from 48 volts DC. Most of the LED lighting, particularly the low voltage 12 volt lighting, they are operable from DC, positive or negative. So this gives you a lot of options to come up with better converters where you don't need the inverter. Next, please. So now refrigerators are there with DC operation. And now if you look at most of the modern inverter driven white goods, inside there is a DC bus as shown in these two examples, where you take AC input, go through a rectifier, get a DC bus, and then for running the compressor motors, you have a DC to three-phase inverter running brushless DC motors, etc. So then for low voltage DC motors like fan motors, you can feed directly DC. Then in washing machines and dryers, etc., you could have brushless DC motors and various other types of things where internally total DC bus is used. So because of these things, DC microgrid is becoming a reality today. Okay, now if you look at normal electric goods operating from 230 volts DC, first stage is a 230 volts DC to a AC-DC converter, and then you have DC-DC converters. But whenever you have renewable energy coming from a DC supply, you can feed that directly to the DC-DC converter, removing one converter stage, which means you can save 5 to 10% energy. And when you use renewable energy, you see no electricity bills coming at the end of the month. So now with less number of DC converters, your total efficiency of the systems increase. And this is why IEEE was promoting DC at home standard within the last several years. Next, please.
I think that's where I'm going to step in again. Okay, thanks, Nihal. Yeah. Okay, so now Nihal has been talking about the DC microgrids and where it's heading towards. So now I'm going to break into where we are at the SCASA applications and then how it's going to fit into the DC microgrid. So giving you a bit of overview, and then I will talk about the actual our research work. So like with the talk of DC coming as like replacing the existing AC the grid. So that's where like you have a much more scope for DC to DC converters, where like the less conversion stages and still the DC to DC conversion stage should be there. And also if we're going to use the existing AC, the products in our like the utility side, so still we have to have AC, so where there's an option for invert applications with the high efficiency. So with all this, so actually our SCASA applications, so the non-traditional supercapacitor based applications, we have DC to DC converters developed and the inverters and the surge absorber and also LED lighting and so on. So I'm going to go into that discussion now. So like our SCASA applications, which we call so based on the theory called SCALoM theory, actually, like the first thing that was what we discovered was the SCASA applications. Actually, we worked through the SCALDO technique and the SCASA technique, where SCALDO is a DC to DC converter, SCASA is a surge absorber. So then after working through these two techniques, so we discovered, so there should be something behind all this, the advantages. And like as a consequence, we found out, so hey, we are doing something for the RC loop. So that's why we see this advantage of all this, the supercapacitor based techniques. So that's how we developed this SCALoM theory. Actually, the techniques came first, and then later on we were able to investigate, so what is the actual theoretical background behind it. So I'm going to go through the SCALoM theory first, and then come to the applications which we started at the beginning, and then our ongoing applications. So like the theory behind this one is, what we're doing is, you know, like the RC circuit loop. So the simple RC circuit. So if we use a simple RC circuit, and then so if it's uncharged capacitor, if we charge from a supply, so then half CV squared is the energy wasted through the resistor, and then half CV squared will be stored in the capacitor. So like now this resistor could be like the internal resistor, loop resistance, and so on, and but it's all together 50%. But if we put two resistors, and then one could be a useful one, instead it could be any useful resistor. So in that case, so out of this 50%, so instead of the dissipation only, so we can use it as an effective the resistive element, so which could be a heater and or a DC to DC converter, or anything as a useful device. And the other thing which we discovered, like, so instead of using the capacitor from the uncharged capacitor, so if we are using midway, like the capacitor with a certain amount of energy in it, and if we are using the charging through that capacitor, so the overall charging efficiency is not as low as 50%. So it's a much better value. So this right here, so which explain, like, so instead of so let's say if we have a capacitor, so which has a voltage about kVW, so which is the initial voltage. So if we're going to charge it to VW, so within that time, so we can write the equations for the capacitor charging, and then we can write the amount of energy stored in the capacitor itself, and the amount of energy that was dissipated through these two resistors. So the R here is together RP and RL. So what we found out is based on the source, so we make the source is much bigger than this voltage. So that's why we use a factor M here. And the K is the factor where the initial voltage of the capacitor, so which is a value less than 1, and then M is a value bigger than 1 to do this charging process. And what we found out is, so this is the charging efficiency if you use this scenario. So from charging the capacitor from kVW to VW, so the charging efficiency we can express as this. So now we're going to combine this with the idea the earlier, so where instead of the wasting energy through the resistance, so we are going to put a useful resistive load into the loop. So at the same time, so the capacitor not at the uncharged stage, so it will be in the intermediate stage, but still it's getting charged with a useful resistor in the loop. So all in all, what we could say is, altogether this is the ratio. If the RP is the resistor in the loop, and RL is the ratio of the useful load. If it's 1 to 9, so you can see the normal case where it's only the RP, so you can see the charging efficiency in the bottom curve. But if you make the useful load is the bigger portion, that means you're using the useful load effectively. So that's the whole idea of all this, the SCASA technique. So we are using a capacitor and in a charging path where it becomes a normal RC circuit. But so in all this, we are using a useful application in that RC circuit loop. So where we keep the charging efficiency at the effective value instead of maintaining it into a low value. So now I'm going to start with our first application, which is the SCALDO technique. So that's where we use the linear regulator, which is a low dropout regulator, as the useful load. So the DC to DC converter is the useful load in the RC loop. And then we use the supercapacitor in the same path. So in this diagram here, so now this is the supply and this is the capacitor, and this LDO part is the useful load. Still it has bit of resistances here and there in the ESR and all this, the line resistance and all this stuff. So which makes the idea of the SCALoM theory. But now here we use the SCALDO idea, which is a supercapacitor-assisted low dropout regulator, where we use the capacitor in the series path and then making a RC circuit loop. So what we found out, so if we use this idea, so what we are effectively doing is we are using the capacitor as a voltage dropper. So normally, like if you use, instead of a capacitor, if you use a resistor in this path, you actually ultimately lose that amount of energy as the heat. But if you use a capacitor in the voltage dropper path, so you store the amount of energy in the capacitor. So what we could do is the initial cycle, you can charge a capacitor putting in series with a low dropout regulator. And the next phase, what you're doing is the amount of stored energy will be used as an energy source for the LDO to the operation. And then that's where you're going to disconnect the supply and use that stored energy. So if I'm going to show the maths around this one. So what we did is, so for the LDO here, we use the commercial LDO, which has the commercial IC, which we use a low dropout regulator. For example, let's say if you're going to do a 12 to 5 regulator in this case, so we use a LDO regulator, which is operating like the 5 volt output, maybe like which can be operated from 5.3 to 5 volts. So which has a very low dropout. So what happened is, so then we're trying to keep the input of a LDO, that the minimum voltage. So the rest of the voltage, so let's say we are going to use a 12 volt battery or the 12 volt supply. So the rest of the 6.7, which we can maintain across the supercapacitor. So what we're doing is, when this is operating, so we always trying to keep the LDO to work for its minimum point. And from there, so we use a like partially charged capacitor, like we showed in the SCALoM theory. So the advantage is better when you use a partially charged capacitor. So we use a partially charged capacitor and then put in the series path with the LDO, and then we let this one to charge. So when this is charging, so the LDO, the input voltage, so when this gets charged, so the input voltage of LDO, so which goes the further down, so and then the minimum value is the V in minimum. So when it comes to that point, so we will switch over to the next discharging arrangement. So the energy stored in the supercapacitor will be discharged into the next stage. So by doing so, what we are effectively doing is the amount of the current taken from the supply is the half the usual current, because normally we have to take the load, whatever the load current IL, but for the charging cycle, we take that load current and charge the supercapacitor. But in the discharging phase, we are not taking the current from the supply. Instead of we using the supercapacitor as the energy supply. So effectively, we make the average value of the current, the half the value. So in that way, we effectively make the efficiency higher, because the amount of the power in and power out, we're still doing the regulation action, and the amount of the input power is effectively, it's the half the value in the ideal case. So that's the basic idea behind this SCALDO. And so actually we've been developing this one over last 10 years. And then we have developed so many different variations of the regulators. And the most common one which we work through is the 12-to-5 one, because normally if you use a 12-to-5 linear regulator, so it was about 42% the efficiency. So it's 5/12 into 100%. That's what you see in the normal linear regulator. But effectively, if you use the SCALDO idea, what we found out, so we can make it the maximum to twice the value in the ideal case. But when you develop the actual prototype, so there are some other, like the loss components altogether. So this is what we were able to get from the prototype. So we did the prototype version of 12-to-5, and actually we developed this idea for further developments, like so the very common the DC to DC converters in the common the portable device power supplies, like 5 to 3.3, 5 to 1.2, and so on. And then we developed this whole initial idea into different set of how we can actually use instead of a just single supercapacitor, how we can use the switch capacitor idea into the same thing. But actually this is not the variation of a switch capacitor. The SCALDO idea is completely different, but when you are using in different the other configurations, we can integrate the switch capacitor, the concept, and then make it work for various configurations. And so later on, we had further the different variations of SCALDO called the reduced switch, because initially for the first fundamental idea, we had to use 4 switches. So for the MOSFET just to switch between the stages. And then, so the reduced switch SCALDO, we managed to make it to 2 switches, and then use 2 LDOs enabled at different stages. And also we further developed this idea for a split rail regulator with the positive and negative rail supply. And all these things happened through the several, actually this happened through 2 PhD stages. And also there was another PhD which was taken as a part of stability analysis of the SCALDO. And also we're happy to say, like, there's a silicon implementation of SCALDO is also available with us. So it's currently at the testing stages. And then, so then after we developed the SCALoM theory, and then we found out we can apply the same SCALoM theory for various other power electronic applications, which may be much more useful in the DC, the microgrid scope. So one thing that we recently worked out is to use, instead of the LDO, now we use a PV inverter. And then we were able to use this idea to use a single inverter and to make the input range wider of an inverter. So instead of having, because we know when there's an inverter comes, so it has a certain operating range for the input. So by putting a supercapacitor at the front, like what we did in the SCALDO idea, so we can see, like, we can expand the input range of the inverter. Like, we can use the same inverter for a different input range, but still we can maintain the same efficiency of the inverter. And also we can integrate another useful thing into this concept, putting a relatively large supercapacitor, so where we can integrate the DC UPS capability. So whether when there's an interruption in the power supply, so we can use this supercapacitor to keep the maintaining the UPS capability for the inverter as well. So that's something that we currently develop some prototypes. And then, so this is some of the work, and another PhD student is working on. And so like we found out there are several variations of this inverter idea, where you can use a single inverter and then extend the input range, or we can use just instead of the specification of a single inverter, we can divide into sub-modular inverters, and which we call the SCASMI idea. So there's another student is working on this idea and developing the mathematical the theory behind this one. So what we initially do is like similar to the SCALDO idea. So we have the RC loop where you have a supercapacitor and an inverter in the loop, and then which is charging from the supply. And there will be another stage where a supercapacitor will be discharged to an inverter as DC supply. So we combine 4 of these stages to get the required output. So by the look of it, you may feel it seems a bit bulky with compared to what we have in general, but the whole idea is to make the compact inverter stages with the high frequency transformers. And so the whole advantage of this one, by the making the 4 stages, what we could do effectively is we can make the current through each inverter module is half the original value, so which ultimately we can make the conduction, the MOSFET conduction loss smaller, and at the same time, so we make the voltage half of the initial value of the inverter from the DC input side. So in that way, we make the effectively make the RDS on the value of the MOSFETs in the inverter H bridge. So which is, so based on this equation here, which has a nonlinear relationship, effectively that we make it smaller, and also the winding losses of the transformer smaller because of the induced voltage, the voltage becomes smaller, and then the number of turns becomes less and the resistance become less, so the winding loss becomes smaller. So we have developed a prototype version which we found out like we can get a very good efficiency advantage for the prototype which we developed compared to the one from the original inverter. So there's a lot of initial work still going on in this area. So now I will pass on to Nihal. I think we have a couple of more minutes. So Nihal will be talking through the other 2 techniques, and we still have lots of other techniques. So we only took 4 to discuss today. Yeah, so over to you, Nihal. I think you're mute.
Can you hear me now?
Yeah.
Okay. Now, all what Kosala did in the last few slides is to show that whenever you take a simple textbook RC circuit, replace the resistor with a useful power electronic building block like a DC-DC converter, inverter, heater, LED light, whatever, and then replace the capacitor with a million order larger capacitor, which is a supercapacitor, you can come up with a total new family of converters which can be used to bring higher efficiency converters which are quite close to the efficiencies of high frequency switch mode converters. Now, one good thing about all these supercapacitor assisted converters are that they run at fractional hertz to millihertz order frequencies. Okay, now what I'm going to show in this slide and the next couple of slides is few other different applications. Now, almost 2010-11 period, I had the new PhD student working on the capability of supercapacitors to absorb lightning surges like very high voltage, short duration, transient surges. Now, if you take a 1 microfarad capacitor with a 1 ohm resistor, your time constant will be 1 microsecond. So if you have a 50 microsecond wide surge of 1000 volts, the capacitor will try to charge within 5 microseconds to nearly 1000 volts, and that will get destroyed if the voltage rating of the capacitor is less than 1000 volts. But if your capacitor of 1 microfarad is replaced by a 1 farad capacitor, your circuit time constant will become 1 second. Now, for a 1 second time constant circuit with a 50 or 100 microsecond transient surge voltage of 1000 volts will not charge the capacitor to the rated voltage. What we found was, based on this simple concept, we found supercapacitors can be used in surge protectors. Next, please. So actually, with our 2011 IEEE journal paper published about the surge capability of supercapacitors, we jumped into apply this SCALoM theory into surge protectors. So which was a successful endeavor, where ultimately we were able to file a patent called SCASA, and one of the Australian companies from Perth, Tor Technologies, they have come up with our technique converted to their smart TV IQ surge protector based on this concept. Next, please. So now this is a traditional surge protector on the second row of the figures to absorb common or differential mode transient surges which should not flow into a critical load like a computer or whatever. So in these ones, people use metal oxide varistors, LC filters, and bidirectional breakover diodes to absorb the transient surge. Now, if you try to use a supercapacitor, we can't just replace at the places of M1, M2, M3 or T1, T2, T3, because these voltages between live to neutral is about 230 volts, which means a peak of 325. Whereas a supercapacitor will be about less than 3 volts rating, so it is not usable. But because of their surge absorption capability of the long time constant circuit, we can use a circuitry to come up with a surge protector which has much less components than this particular traditional surge protector. Next, please. This is what you show at the top of the figure. In the middle of the top, this thing, this is the SCASA technique, which is a very simple thing. One metal oxide varistor, one supercapacitor, and a coupled inductor will do the job of absorbing transient surges. And when we proved this in a PhD project, that project was translated to a commercial product by the Australian company called Tor Technologies. What you see on the right hand side is the commercial product they sell in Australia now. Now, table 5.4 below compares various types of traditional surge protectors and the SCASA technique with regard to number of components, and you see number of components in SCASA is much less. And the bottom graphs show that clamp voltage of the SCASA technique compared to traditional surge protectors is also much better, which is about 200 to 300 volts less. So all in all, this SCASA technique is an extension of that same theory. The number of components are less and the transient related voltages at the protected load is less than the clamping voltage of the MOV. In a traditional surge protector, what you see at the load end is metal oxide varistors clamping voltage is observed at the load. But in SCASA, we can get less than MOV's clamping voltage at the load to get a better protection. So this was a very successful extension of SCALoM theory and a SCA technique. Next, please. Okay, now one of the more recent PhD projects we went with the SCA Techniques was to come up with LED lighting and supercapacitors combined into a SCA technique. In doing so, we use 12-volt LED lights where their luminance level is constant for a wide range of DC voltages from about 5 volts to 20 volts for different brands of these things. Then we extended that SCALoM theory applied to the RC circuit to feed DC bus coming from a DC microgrid in series with the LED light with the supercapacitor module. Next, please. So this is what we do. Whenever you have a building LED lamp load, you divide it into two halves. You take one half of them in series with the supercapacitor bank, identical to supercapacitor bank. One of them run in series with the LED lamp load fed by the solar panel. Then the pre-charged supercapacitor bank of the same size runs the other half of the LED lamp. So this is a very simple explanation of SCALoM technique. If you want more details, there is a journal paper now released to IET Power Electronics to give all the details. So this project we did with the pilot grant from Ports of Auckland Limited. So we had now installed a working prototype in the Ports of Auckland, because this technique is directly applicable all sorts of LED lights, including high power LED lights people use for warehouses and street lights. So next, please. So if you try to take a summary of the SCA techniques which we described in this seminar, the first thing we did was SCALDO, which we started in 2008, which we have now gone up to a single chip silicon implementation with the collaboration from Southampton University. Then SCASA surge protector, which we started 2011, it is a commercialized product by an Australian company. Then we had another technique which we didn't describe, rapid water heating, for eliminating the hot water delay in our home, these things, which we did with Rina in New Zealand. This technique is called SCATMA. The LED lighting technique, SCALED, which we started in 2006, now it's a finished PhD, which we did for Ports of Auckland, and it is now installed in demo container. Now these inverter techniques and so on, what Kosala described, is done at AUT in our collaboration. This project was inspired by the Google Little Box Challenge. Next, please. So in conclusion, when a capacitor becomes almost 1 million times larger, it can be creatively used for very new circuit topologies and techniques. These new techniques can help in high efficiency power converters, surge protectors, rapid heat transfer, high density inverters, DC microgrid applications, and very many other things. In fact, it's very interesting. Over the last 12 to 15 years of work we started at in New Zealand, every 6 months we see a new application of these car techniques. So we are very enthusiastically developing it, and we have an open invitation to many people to work with us on collaboration, because you have a lot of real world new topologies to be built, and the people who are interested in publications, you have a lot of openings. So what you saw in this seminar is the tip of the iceberg. Creative circuit designers can use commercial supercapacitors in many different applications than simple energy storage systems. This is the ultimate conclusion. Kosala, feel free to add something to the conclusion.
Oh, yeah. So I think Nihal put everything together. So actually, we are working on developing a DC circuit breaker with the supercapacitors at the moment. So that's the initial work that Nihal and myself, we are working on with some PhD student in both universities. And like actually what we see all in all in the SCALoM theory, which we could apply for many power electronic applications. So that's like we are trying to like take one at a time and then go on there. So that's where we are, and we are quite happy to take collaborations from people, especially across the ditch, because we are kind of in the same part of the world and we can easily communicate. So that's part of like the putting this webinar towards the Australia. So that's part of, we like to have some more people join with us and doing like some of these like non-traditional supercapacitor applications. Okay, so I saw there was a question. Actually, I think it was there was a question which is about a typo in the slides about. So I don't know whether I can say it now.
Yeah, you can just go ahead.
I can't see the chat window actually.
So basically, Rick asked about the a small can, 2.7 volts can generate around high power, like
actually,
kilowatt range. Yeah.
I saw it earlier, but no, I can't see it. Actually, it was like it was like whether it's a typo or not, right? So
Yeah. So
I will
basically,
go.
on your slide 6, slide number 6.
Yeah, I will go
when you
up.
do the comparison. Yeah. So for all, we can have some quick question while Kosala is preparing, so you can type it on the Q&A on
I
chat
got there.
box.
I think this is the one he was referring to, right?
Yeah, the first one.
Okay. So what was the question actually?
Oh, the question is, can can you generate such large power? Because you are talking about, more than 1,000 amps, of that. Because
okay. Let me explain, answer that question. Now, we have uploaded the YouTube demo and another video to Power Electronics Society website in my previous Pell Society webinar. A 3000 farad symmetrical supercapacitor of this size, if you fully charge it and try to put two aluminium strips here, when you try to short circuit them, in less than a minute the metal completely melts and pour down. So in that short circuit, you are pushing easily several thousand amperes from this 3-volt source. So the reason is the internal resistance of this capacitor is about 0.3 milliohms. So if you divide 3 volts by 0.3 milliohms, that translates to a starting short circuit current of 10,000 amperes. So actually, when you try to short circuit with a steel or a aluminium piece, that melts. You can cut and drill metal with one single supercapacitor of this size.
Very useful. We have another question from Chris. So he said that when you use in the surge absorber circuits, do you need a few hundred, supercapacitor in series to get the required voltage rating? So
no. We use only one single 2.7 volts capacitor in that circuit.
I will go down there.
Yeah. Okay. Yeah.
Okay.
Next one. Now, if you look at the circuit slide here, the supercapacitor placed here is not across the line to neutral rail. It is placed between this coupled inductor's secondary winding. So this is one single tiny supercapacitor of this size. Actually, in the surge protector, what we have used is a single 2.7 volt supercapacitor to assist the surge into the combination of these components and dissipate it quickly. So this uses not a supercapacitor set in series, one single 2.7 volt supercap.
So how do you make sure that the voltage, does not exceed, that small voltage?
Okay, to understand that, if you refer to our 2011 journal paper, which Kosala, can you just roll down to that?
Oh yeah, the paper that you mentioned.
That gives you all the details. In this paper, we show why the theory allows you, because if you look at the capacitor and the resistor in series in the RC loop, the time constant is so large, during that 5 time constants or less period, most of the voltage will be dropped across the resistor. So we use the supercapacitor as a aid to dissipate surge energy in a resistor. Surge energy is not going into the supercapacitor. Supercapacitor is used in a very tricky way to short circuit the energy into the resistive loop. So that way you don't need the bank of supercapacitors. One single supercapacitor is very easy. So this is a very cool technique. That's why we were able to commercialize the thing very quickly.
Yeah. So follow on that, actually, Paul, we have 2 questions from Paul in the chat box. So maybe you can answer that. So that's for DC microgrid, how do you overcome a couple of problems? First, the corrosion due to constant potential difference. The second one, accretion of dust, etc., to the line connector at the non-earth potential.
Which question?
So if it's a question on the chat box.
Yeah, okay, I can see. Is it regarding SCALDO concept? Can it be shown to be significantly more efficient than buck mode SMPS? Is that the question?
Yeah, I saw that one.
Yeah.
Oh, there are 2 places, right?
Yeah. So the 2 places now. Sorry about that. Yeah. So So the first one is actually so like the corrosion. Do you have any corrosion problem due to constant potential difference? And the second question is accretion of dust, etc., to the line connected to the non-earth potential. So if you look at the chat, in the chat, not the Q&A, the other one.
It's chat. It's there. There's a question for you. Can you please answer?
Right. Okay. Corrosion due DC bus related corrosion due to constant potential difference. So the way to get rid of it, I mean, every say couple of weeks, you can interchange the DC bus wires by electronic means or otherwise. The second question, does the supercapacitor have good enough frequency characteristics to handle high frequency steep wave front surges in transients? Actually, supercapacitor is not handling it. It is the 2 coupled inductors coupled with the MOV in the SCASA circuit which handles the steep wave front surges. Supercapacitor just assists it by making a short circuit across these things, the surge only. 230 power passes, surge gets sucked into the coupled inductor and the MOV and the rest of the sub-circuit.
Oh, yeah, I can see there are some questions in Q&A.
Yes, if we can answer them.
SCALDO concept, can it be shown to be significantly more efficient than a buck switch mode SMPS? So what we found out in the prototype, so the efficiency which we could get was pretty much closer to the numbers of SMPS, but the other advantage of SCALDO is all this supercapacitor switching was operated at very low frequencies. Actually, our frequencies was millihertz and hertz range. So that's the other advantage of SCALDO. So when we're switching from the charging to discharging mode and coming back and going on cycling, so it was like very low frequency. So therefore we don't have any RFI ME issues with the SCALDO compared to the switch mode. So we are pretty much closer efficiencies and has a added advantage of RFI EMI advantage as well without having those issues.
Can also at one point is because you have the LDO at the output, right? So in
Yeah,
this
yeah.
case, the output response is quite very quick. You know, it can be as fast, even faster than the switching power supply in general.
Yeah, that's
So
the slew rate. Yeah.
So you get the advantage of a linear regulator and removing the disadvantage of low efficiency by the
low efficiency.
supercapacitor technique.
So there's another question.
From Jahenga, yeah.
Nihal,
Okay. To answer that, Jahangeer Hossain.
Jahenga Hossain. Yeah, he's our colleague.
Right.
Yeah.
Okay. Actually, the DC microgrid application for LED lighting for the ports, we were using this type of supercapacitor based modules because at that time these things in module form were not available. Now they are coming into the market. So these can be used. It's no problem, but they are now only coming into commercial form as modules, Kappa battery modules.
And then from Lindsay, how do we define a life cycle? So, like, the lifespan, of the supercapacitor.
Okay, very simple. You fully charge the capacitor, discharge it fully, keep counting the number of cycles until the capacitance drop to 80%. So when you drop the capacitance to 80%, you consider the capacitor is to be thrown off. So it is full charge discharge cycles until the capacitance drop to 80%. So I think it's the same definition for a battery life cycle.
So in terms of comparison, do you have any numbers that, how long, was the lifespan, of a super cap or hybrid cap? Yeah.
Oh, we had that numbers here, right? In the slide.
Oh, yeah.
The other thing, like, because for SCALDO itself, we have like close to more than 40 publications so far. And then so all these are available in IEEE. I think we have about 6 journal papers of SCALDO itself with various the other work that we did. And so all these, the other techniques, we have some IEEE journals and conference papers, so which more details are available for you to refer. Yeah,
you do have that in the table. So if you don't mind, I can share the slides with the the audience attendees, so they can have a good look, read of the slides, and maybe can contact you for further questions.
And also, Dylan,
yes.
While I was doing this seminar, I dispatched you a very recent IEEE journal paper, which got published in the Industrial Electronics magazine. About
I saw that. I read that. Yeah.
Right. So you can share that with all the participants. Because this is publicly available in the magazine. So, but if you want to share the e-copy, please do so.
Yeah. So yeah, I'll definitely do that. Thanks so much. Kosala and Nihal, given us a very, very interesting, inspiring, application of supercapacitors. And that is so great. I mean, in particular for my students, in particular, they see that it's not just publication, right? But moving on to the next stage where you can commercialize and making a product, and we can benefit more people, which is actually, to me, is so great. That's the aim. One of the aims that while we are doing research. I think.
In fact, one thing I had last at this moment. Most of these techniques are now understood by several supercapacitor manufacturers, including Worth Electronics Germany, Vinatech Korea, Samwa Electric Korea. Those people are now giving us samples and everything all the time, so that they encourage us to develop these things, and hopefully we will be able to come up with some collaborations with these companies in the near future, because we are in that discussion at the moment. So there's some commercial opportunity for collaborators.
Yes. Yeah, good on you, man. That's so great to hear. We like to hear from you again. Maybe in a few months' time. You say after 6 months, right? You have a new application. Maybe we can have another seminar to give more detail.
Definitely, when we get to the DC circuit breaker,
Yes.
So it could be very interesting.
Yes.
Yeah.
Yes. Definitely, yes. So anyway, I'm way out of time, but but it's so great, to have you guys here, and so great. Thanks for all the attendees, for your great questions, and
There's
yeah.
somebody from Virginia saying this was terrific.
No. Awesome, Steve. Thank you very much for joining us. From the US. Yeah. All right. So yeah, thank you so much. And then I have to close it. And if you have further questions, please contact Nihal and Kosala for further questions. I will send you guys the link for the recording as well as the publication Nihal mentioned. So bye for now. Hope we'll come back for more webinars. And thanks for support. See you guys.
All right. Good.
Okay.
Thank
Bye.
you.
Have a good day.
Bye-bye.
Bye. Bye.
Bye to all.
Bye.